Hello, everyone, and welcome to today's OpenTeams community event. OpenTeams is a single point of contact and procurement for your open source solutions, support, and training needs. Visit openteams.com or reach out to us at connect@openteams.com to learn more. As part of OpenTeams' overall mission to sustain and support open source, we are also sponsoring the open source architect community with the goal of providing a dedicated space for experts to connect and collaborate over their favorite open source technologies. To learn more or to apply for membership, visit openteams.com/OSA-community. Today, Nick Muoh is going to give a talk titled Into the Logisticverse, Improving Efficiency in Transportation Networks Using Python. He'll discuss the complexity and dynamic nature of transportation networks and explore some specific Python tools and their applications in this space. I'll leave a detailed introduction on that to Nick in his talk. A quick note first, this event is a bit of an experiment for us. Nick actually presented this same talk earlier this year at PyCon US in Salt Lake City. So that part of the event content is something that is already out there. But a primary goal that we're trying to explore with this event is to give folks an opportunity for longer, more detailed Q&A and discussion with Nick on his talk and the topics in there. So please post any questions you might have during the talk to the Zoom chat or Q&A. And if anyone is interested in talking directly to Nick, asking your questions directly, engaging in conversation after the talk, we can bring you on stage either audio only or full audio plus video, your preference. And if you're interested in that, let me know in the chat. So, all right, let's get started. Nick, hi. Good to see you. Thanks for being here.
Yeah, thanks for having me.
Appreciate you taking the time to represent what you've been working on here. So before you bring up your talk, can you give us a quick intro on you, on your background, education, career arc so far?
Yeah, sure. Actually, I have I have some visuals to help aid in that discussion.
Cool.
So I was gonna quickly share my screen here. Can you see me?
Mm-hmm. All good.
So yeah, as Brian said, my name is Uzoma Nicholas Muoh, but people refer to me as Nick. So you can think of me as your friendly neighborhood data nerd. My journey kind of started out at Universitatea Politehnica din Bucharest in Romania when I was getting my bachelor's in computer engineering. I had a pretty bad experience learning Java and all the coursework related to computer engineering. And then I discovered Python, and it was like a breath of fresh air. It literally just fit my brain. All the problems that we were trying to go through in school just fit nicely when I was writing Python in it. And from there, after finishing my bachelor's, there was a point in time where there was so much buzz around data, AI, ML. Google was releasing these new models. TensorFlow was coming up. All these things were coming, and it swept me off my feet. And so I found an opportunity to go get a master's in data science at Kent State University. So that was my first entry into the world of data, doing that master's. While I was there, I did find community, a local community, CliPy. So we have a meetup group, which I help co-organize as well. You can see me over there. And that really solidified my my experience using Python. So Python became less of a language and more of a community for me. And I think like Brett Cannon mainly said that he came for the language, but he stayed because of the community. That was my story as well. Once I finished my master's, I got my first start at I got my first professional start in Trimble as a data analyst, and from there I've been there for like 4 years now, working in the transportation industry. Yeah, so that's me.
Excellent. Yeah, great background. Setting the stage for the technical material you're gonna switch to. So. Take it away. I would say just go ahead and dive right into to the technical presentation.
Yeah, of course. So welcome everyone into the Logisticverse. We'll be talking about improving efficiency in transportation networks using Python. Now, transportation is an industry that, from what I've been told by Tyler, Hoff, and Brian, is not one that's often talked about in the OpenTeams community. I was hoping to reshare my talk here in order to give the OpenTeams community a little bit of intro into what we do in transportation, at least the crux of it. There's lots of things, but at least the crux of it. But before I get into what we do, I just want to establish some facts about how substantially impactful transportation is to the US economy and to most economies, but I'm going to focus on the US economy for now. So 1.26 trillion is the amount dollars is the amount contributed by the transportation industry to the US GDP as of 2022. 875.5 billion is the annual revenue of the US trucking industry in 2021. So it's important to really keep in mind that the transportation industry incorporates a variety of businesses that operate within different modes of transportation. So that means sea, railway, air, and these businesses within transportation, their main butter is to just provide a way to move goods from one point to the other. In this talk, though, I'm going to focus mainly on trucking because that's where my experience really is in. And the trucking actually makes up a really large portion of the transportation industry's activity, actually. So 72.5% is the market share of freight moved in the US by just trucks. 10.9 billion tons of total weight of trucks is transported by trucks in 2021. 24.5% is the amount of fuel consumed from commercial trucks. So America has this reputation of being the land of cars because cars was a symbolism of freedom. Trucks and commercial vehicles, vans, your UPS driver, they drive much more, and they constitute the most of the fuel consumption in the country, which is kind of crazy when you think about it. So the problems that the trucking industry face are what my team in transportation work on day to day. Today, we'll dive into the problems and their solutions, and we'll specifically focus on over-the-road trucking. So what is that? So these are known as long-haul drivers, right? So a type of trucking where drivers transport goods over long distances, such as interstate or international routes. So think of the semi trucks that you see on the road that sometimes can bully you, or are really transporting really critical products for a city or a town. These are the people that you should think about. With that being said, I think we should get into knowing who are the main stakeholders at the heart of the problems facing the trucking industry. So I'm going to start off with carriers. Examples of these are JB Hunt or Landstar. I actually often find myself playing a game where I am driving and I notice a truck and I notice their brand and say, hey, I know these guys. So these are carriers. So what do they want? First, what are they? So these are companies that pick up freight from a location and deliver it to the destination. What do they want? Well, they always want more customers or more orders. They want fewer empty miles. Every mile a truck travels without any load costs the carrier money, right? You're not getting paid for that. Keep existing drivers and hire new ones. The turnover rate for long-haul drivers can reach more than 120%. Keeping drivers happy is a high priority for carriers. So for many businesses, turnover is really costly. In trucking, it's a serious problem that they're trying to fix. So that's one of the problems that carriers care about here. The next are shippers. These are companies that need their freights to be moved. So think of Nestle or P&G. So whenever your local DiGiorno pizza is in your local grocery store, it's Nestle is Nestle the shipper that made sure that those products get there. Like, no, they are the ones that have that need to get that products get over there. So what do they care about? Availability of trucks and drivers to deliver their freight. Nestle wants people, wants carriers, wants trucks, wants drivers that they can move the vast amount of products that they produce. They want cheaper rates, obviously. And now coming to drivers, who are they? So these are either owner operators, meaning they own or lease their own trucks, or they are employed by a carrier or a broker. For them, what they want is pretty simple. They care about their pay, they care about their time, and they care about being safe. So given all these different perspectives, where does data science come into play? Well, it starts with understanding the business problems of these different perspectives, after which collection of data, utilization of it within a data analytics and ML framework can yield solutions that actually address concerns of these perspectives. So let's start looking at the carrier network. So this visual here is a nice representation of a carrier's business. If there are areas of the network that are the cause of waste or low driver utilization, then it affects the entire business of the carrier. However, improving efficiency of carriers' network does not only involve optimizing specific business metrics such as revenue per truck, per week, or freight order velocity, but it requires a more holistic approach that takes into consideration how well and connected a carrier network is. So looking at the carriers network I have on the screen here, it kind of looks like a graph data structure, something that you would probably learn from a computer science course. Well, if we treat a carriers network as a graph structure, then we can obtain a better macro level optimization for improving a carrier's business. Now, so this is where the term graph analytics comes into play. So it's a type of data analysis that focuses on studying relationships between different entities, which could be products, customers, or even devices. A graph for a carrier network could theoretically be as simple as this. You have nodes, which represent geographical entities or areas or cities, or however you want to cut it, and an edge. But in the context of transportation, we refer to these as lanes. Essentially, it establishes a relationship between one node and another, and it determines freight activity. So if there is a lane between one area and the other, it means that there is freight activity between one area and the other. But in reality, this graph network is pretty simple. Right now, what you're looking at is an undirected graph. And in reality, most carrier networks are directed graphs. So they look something like this, where you have something like Texas to California. There is an arrow pointing from Texas to California. And within there, a carrier could have done a revenue of $5 on a distance of 200 miles, which is terrible, by the way. Or the opposites, where they could be doing revenue of $4 on 100 miles, which is also terrible too. Obviously, an actual carrier's network is a lot more complex than this. A carrier's freight activity for a couple of weeks could generate really complex graph data structures. So how would we begin to analyze and optimize a graph data structure? Well, this is where the Python package Network X shines. So let's try creating a graph using Network X and some carrier freight activity data. So I have this sample toy data here that specifies where a pickup and delivery and some costs associated with it. So we take that data and load it into a pandas data frame. We specify the data frame as a parameter to network X using the from pandas edgeless function. We specify the source and target nodes as well as the cost as an edge attribute. We indicate to network X that we're building a directed graph. And finally, we draw our graph. And then we get something like this. So, sorry, hold on a second. Oh, sorry, my whole presentation. All right, okay, so I'm back again. Sorry about that. Now, this is the graph that we created. This looks great, but there are some peculiar aspects about it. So I took the liberty of highlighting those edges that point to nodes that are marked as that are marked in orange. These are what we call leaf nodes. So we could write some code to like find it using network X, and these are essentially nodes that have an out degree of equal to 0. These nodes are what we call leaf nodes. These leaf nodes are a point of inefficiency for the carrier. If a driver delivers a load to one of these nodes, then in order to get out of that node, they would most likely have to travel with no load to somewhere else where they can pick up another load. So they are driving empty and they are not being paid for that. So the driver doesn't get paid and the carrier doesn't make any money. So that's not good for them. Aside from the business impact of these leaf nodes, they also harm the connectivity of the carrier's graph. And there's actually a way we can measure that. So if we look at the graph without all the costs associated with it, we can actually borrow a concept from graph theory called connectivity, which is a measure of how strongly connected the graph is and how many paths there are between any two nodes. We can measure connectivity using the alpha index and the beta index, where for both, the higher the number of the index, the better. Let's calculate these measures for our graph. So what we get for alpha index, it's 1.43, and for the beta index is 0.2. What if we suggested that a carrier not operate on these edges and we just remove it from the graph? Essentially, if a carrier has a hard time finding load out of one of these leaf nodes, what if we just say, all right, don't go there, don't go to that node anymore, stay away from it? How does that affect the carrier's connectivity? Well, notice how the alpha and beta index increase. These indexes essentially tells us that, well, now the carrier has a much more connected graph, and a much more connected graph will yield to a more robust business, meaning that the driver now can always pick up new load from any of the nodes / areas they find themselves in compared to before. So this is good. It's a step towards improving connectivity, but what if we wanted to keep those nodes? We didn't want to take them away. Maybe find other edges the carrier could travel to improve their connectivity. How can graph analytics help assist us here? So this is where the idea of collaborative decision making comes into play. Imagine we have aggregated and anonymized data of market freight activity, meaning freight activity of other carriers in the market that a carrier operates in. So let's say we have market data for the whole of the East Coast, right? We could turn such data into a graph data structure, like so. Take the graph structure of the carrier's network we were trying to optimize before. and combine them to obtain a larger graph. Now, using Network X package, we can easily explore the graph to find some paths that minimize some cost. This is essentially the shortest path traversal algorithm in a nutshell. The technique described is a common one used in recommendation systems called collaborative filtering, where suggestions to users are based on the past behavior or preferences, as well as the behavior of similar users. There is so much we could do with graphs, and we have only scratched the surface here. But I would actually like to point out that graphs analytics, although powerful, can only take you so far when it comes to optimizing and improving efficiency in transportation networks. There are a lot of algorithmic solutions and domain knowledge that you would need in order to properly address business needs. What I just went through is just a taste of what you could start doing just using graph analytics. Now, I would like to actually start exploring some of these other problems that we can't really solve with graph analytics. One of these problems actually affects both carriers and shippers. And the main question that this problem problem raises is, how do we efficiently decide if an order is good or bad? Do we just flip a coin? Well, obviously not. It's not that simple. Finding the right order is a pain point that affects carriers and shippers. As part of a shipper's annual procurement process, they submit orders, commonly referred to as tenders, to carriers in the hopes of securing the best freight possible. The volume of orders to evaluate can reach in the tens of thousands on a given day. So for carriers, if you're a small carrier, you don't have that many trucks, and you operate in a busy area, so let's say Chicago, you could get a lot of orders, a lot of tenders that you might have to evaluate, and not knowing which ones to use is it's a dilemma for any carrier, big or small. Now, in addition to these tenders, they also have a time window associated to them. So, and these time windows are actually defined by the shipper, in which a carrier has to either accept, reject, or in some cases counter. So aside from the number of tenders a carrier has to evaluate, there is so much, there's only so much time that they have in order to make a decision. Talk about pressure. If you're a medium or small size carrier, then evaluating each order in the time frame that you have can be a non-trivial problem, a very daunting one. Challenges for this are to be expected, like I said, for any carrier size. So if a carrier, what if a carrier was not able to respond within the allotted time? Well, then the order times out, which is unideal for both the carrier and shipper due to missed opportunities. Now, this risk and opportunity costs associated with not only timed out orders, but also accepting and rejecting an order is something that we try to efficiently evaluate by minimizing the risk and opportunity costs. So that's the key thing. How can we evaluate this? By minimizing the risk of not accepting when you're supposed to, or rejecting when you're not supposed to, and the opportunity cost and the time window related to all of this. Yeah. So to evaluate this, I think it's important to actually think of to have like a useful mental model. One that we employ at one that you can employ is actually called factors, components, and ratings. So the first aspect of this is called a factor. These are variables that influence how good a fit and order is according to the business. The next component is called components. These refer to the specific operational metrics and calculations related to a factor. And finally, we have the overall rating. This is an easy to interpret assessment for the order based on scoring the factor. So let's look at examples of what factors and components are. So one is financial. Essentially, an order should be financially sound and profitable for the carrier. The next one is the next one under financial is called order throughput. This is a component of the factor financial. So with order throughput, what we're talking about here is the revenue minus the total variable cost. Another component is the shipper payment turnaround. So which essentially means the median time in days it takes for a shipper to pay the carrier. So let's look at another example of a factor, order attributes. So when we're talking about the order attribute factor, we're talking about the attributes of an order that meets the carrier's capability. One of those components is equipment type, meaning the type of trailer needed to execute the order is known to the carrier. If a carrier is mainly used to transporting dairy products or livestock, then you can't expect them to be able to execute an order that is transporting biohazardous material, right? Like they can't do that. Each component of a factor yields some value to the business. The factors and components here are just a small example. Depending on your business, these needs can be much more robust. Now that we have defined all these components and factors, how can we come up with a way to rate the tendered order? Well, if you consider how a computer uses traditional Boolean logic would provide a rating, it would take some precise input and produce a definite output, 0 or 1, good or bad. However, human decision-making is a lot more nuanced. Decisions by humans have varying degrees of truth between 0 and 1. So one could say, is this a good order for us? And you could say, well, yeah, it's mostly good. How can we capture that in using logic? Well, this is where the idea of fuzzy logic comes into play, and a very useful package called SkyFuzzy. With SkyFuzzy, we can build a fuzzy logic system that mimics human reasoning. So there are 4 main parts to this fuzzy logic system. We have the fuzzifier module. This takes in a crisp input or non-fuzzy value, so precise value. So think of like a rating, and fuzzifies it through the use of membership functions. Then we have the knowledge base. This stores and maintains the relationship between the if-then rules and linguistic terms. Then we have the inference engine, which simulates the human reasoning by making a fuzzy inference using the fuzzy input and the if-then rules. Lastly, we have the fuzzifier. This transforms the output of the inference engine into a crisp value. Now, let's examine the fuzzy logic system that will rate a tendered order based on the financial factor that I showed earlier. So this is where we're going to get into some code here. We'll start by importing the SkyFuzzy and control module like so. We define the crisp inputs, which SkyFuzzy designates as antecedents, as well as the expected ranges for these inputs. We define the crisp output, which SkyFuzzy designates as the consequence. We define the membership functions that will be used for the fuzzification of the crisp inputs. So this essentially details what constitutes as good versus average and mapping it to the crisp inputs, the actual precise values that you actually input into the fuzzifier. So we initialize our logic system with our rules and initialize our inference engine here. We invoke the fuzzifier, and then we get our ratings for the financials, which turns out to be good in this case. So with all the code we're written, once we pass in the rules and we pass in our fuzzifier and we execute the computes on our fuzzy logic system for the financial factor. Now, you can see here on line 7 and 8, we just input some raw values for order throughput and pay turnaround. These values are based upon how you define your membership functions and how you define the ranges for your input values, right? So this is wholly dependent on your business. So for us here, we added an order throughput of 26,000 and a pay turnaround of 10 days, and the financial output is 76.67. And according to the fuzzy logic system, that is regarded as good. All right, cool. So some noteworthy benefits of using fuzzy logic for evaluating tenders is that it is composable, meaning that you can create additional fuzzy logic systems for other factors and aggregate the results to obtain an overall rating. Fuzzy logic is also explainable, which is a very valuable for the business, because there are no black boxes. You can actually explain what's going on in there. Now, with fuzzy logic system, we can efficiently evaluate an order, and we accepted it. We efficiently mitigated the risk, provided a way to mitigate the risk, and provided a way to address the opportunity cost. And this can all be done within a timely manner. So you're not going to brush up into that time window unless you procrastinate, which sometimes I'm guilty of, to be honest. But you don't have to with fuzzy logic here. Now, we've accepted an order, but now how do we match that order? How do we know, like, okay, we have this order, but which driver do we give it to, right? Because if you have multiple drivers, they all go in different places, they all live in different places. How do you know which order to give to them to, right? So let's say you are a fleet dispatcher working for a carrier, and you are tasked with finding the best match amongst 180 semi-trucks and available drivers with 120 loads. That's a pretty daunting task. Even though you know what orders to pick, like, to know which drivers to give it to is kind of non-trivial here. Now, let's start by to make this problem to be more specific to transportation. I'm going to designate the combination of a truck and a driver as a power, right? You can't really deliver a load, which is some kind of freight, without a truck, and you need a driver to drive the truck, at least until we get self-driving cars. So I'm looking at you, Elon Musk, with your promise of the Tesla semi-truck. Now, the problem becomes, how can I find the best matches between a set of powers and loads? So before we can actually answer that question of what is a good match, we need to quantify the cost of assigning a power to a load. Cost in this scenario refers to the measure of how good a fit a power is to a load. Now, phrasing it in this way starts sounding similar to a type of problem in operations research there's a particular case of the transportation problem called combinatorial assignment problem. Using this well-defined problem class as a framework, we begin solving our initial problem statement by creating a cost matrix. To create a cost matrix, we need to define a function that will compute the cost for every combination between a power and a load. So, given an example cost matrix, for any given power and load, we would want our function to return values ranging from 0 to infinity. 0 meaning that the power is a perfect fit for the load, cost is absolutely minimal. Infinity meaning that the power cannot be assigned to a load, the cost is way too high, so is not a viable choice or a viable match. Coming up with an appropriate formula for computing the cost would require much more business and domain expertise, but let's look at an example of what a cost function could look like. So in our calculate cost Python function, we are summing the multiplication of a score given by these match functions and a weight. The match function driver preference match returns a score that takes into consideration where the driver wants to go, whether the driver wants to go back home from picking up the load. So based on whether they want to go back home or not, that's and an associated weight with that creates a score that can then be included into the cost function. Then on line 18, we are looping over the powers and loads, that matrix of ours, and populating the cost and paving the cost, which gives us our cost matrix. So this is an example of how our function could look like. Our cost function might vary, your cost function might vary depending on your business needs. Now, with our example cost function and cost matrix defined, how do we continue with finding the best matches? Well, this is where we will leverage Google's OR tools package, which provides a main cost flow solver that can handle this sort of assignment problem. The solver represents the cost matrix as a bipartite graph such that there is a source and a sink node at the end of the graph. This would mean that we would need to transform our cost matrix into a format that can be optimized by the solver. So now let's look at some code. Bear with me here, it's quite a bit. We will first start by importing the main cost flow module. If you are using an older version of OR tools, you will have to import the PyWrapGraph module and import the simple main cost flow, but that's in an older version of OR tools. We define the initial edges leading out of the source node. We define the edges between the powers and the loads with their respective costs. So think of the cost matrix that we had earlier. We concat the costs leading out of the source, the costs defined at the edges between the powers and the loads, and finally, the costs leading into the sink, all into one big, nice array. We define the final edges leading into the sink. We also define the capacity and supply for every edge in the graph. We instantiate our main cost flow solver. We add the edges with their respective costs to the solver. We set the supply of each node in the graph. We invoke the solver, and voila, we have matches. In our case, P1, the first power is best matched with the first load, and the second power is best matched with the second load. And the total cost of these matches is 15. This is the minimal cost for these for this cost matrix. The fleet dispatcher will be pretty happy with this now. Doesn't have to rack his brain trying to decide who to match with which power to match with which load, and he can relax a little bit. All right, so that was a lot, but let's switch gears and kind of summarize what we've learned so far. So there's a significant complexity in the problems the trucking industry deals with. Things are not so simple. The problems I face and the solutions I described are really just a seed to how difficult things can actually get. Formulating the problem and getting the data to solve it is really just half the battle. Improving efficiency in transportation can look very different depending on the business needs. Using Python's rich ecosystem of a library, we looked at graph analytics with NetworkX. We came up with suggestions that would improve the connectiveness of a carrier's network, therefore improving their overall business. Finding the right order with SkyFuzzy or skFuzzy. And from using this package, we figured out how to help carriers efficiently evaluate an order. And we looked at the assignment problem with Google's Aura tools. We looked at how to find the best match between a power and a load at the lowest possible cost. All right, so I would like to thank OpenTeams for inviting me to share this talk with you all. And of course, for Trimble for giving me the opportunity to give this talk and to showcase the kinds of problems we solve at transportation. Specifically, I want to thank Brian for chasing me down and getting me ready for today, and Tyler Hoff for really introducing me to the OpenTeams. I literally had no idea this community existed, and I'm looking forward to engaging with the community more. So I have some resources and my socials down at the bottom if you want to reach out to me, and I'm ready for any questions you guys have. Thank you.
Terrific. Yeah, of course, Nick. Thanks. Yeah, we appreciate you coming on, presenting, sharing all this with us, and welcome. Yeah. So we don't have any questions from the audience at the moment. I have a few, though, that I'm curious about. Roughly in order. So going back to the network X and the graphs that and whatnot, have you worked at all with systems that are big enough that you need databases to store the graphs? And so I'm familiar with relational and SQL and the object stores like Mongo, and I know that graph databases exist and kind of how they work. Have you touched those at all in the course of this?
Yeah. So the most popular graph database around is called Neo4j. There are other ones like Tiger Graph. I know that Redis has their own graph called Redis Graph too. And in the cases where it makes sense to use these are when, like I was saying, you have really large graph structures that it's hard to like traverse in memory. Network S is great for playing, like just getting your feet wet with some graph analytics and running some graph algorithms. But when you have really large relationships between nodes, Network X doesn't really cut it. And that's something that I've encountered in the past myself, especially when you want to run like custom traversal algorithms that evaluate how they're traversing the graph using some kind of custom cost function.
Mm-hmm.
Yeah, Network X traversing all of that in memory with really large graphs is not really the best way to go. So yeah, graph database like Neo4j is a very good bet. There are other ones like Tiger Graph, and I think there's also called TypeDB, which is actually, I think that's also another graph database too.
Mm-hmm. Yes, similar problems with any data. Once you start to get too large for a single machine, then you have to start coping with getting the data where it needs to go and getting access to all of it and storing it in a useful format, efficient format. Yeah. All right, Tyler in the audience, he's there, has a question. He says, when there are areas of heavier use for pickup and drop off, moved it. Does that then reinforce those areas being busier, and then the lower traffic areas getting smaller and smaller? Like I think he's like, are there it's self-reinforcing dynamics where busier areas tend to only get busier, kind of self-reinforcing that way, and then less busy areas self-reinforcing, kind of tending to dry up and wither away.
Yeah, that is a phenomenon that I have noticed personally while analyzing transportation networks and looking at market data areas. So an example is like Chicago. Chicago is known for a place to be really busy, heavy logistic place. Also, Ohio Columbus and Ohio Cleveland are places known to be really busy. So is California. And those places generally tend to get busier. Those are places that drivers often are willing to drive to because there's a lot of demand for freight to be delivered there, compared to places like Florida, where most truckers will say that they don't like going there because there's not much freight coming out of there, right? There's a lot of freight going into there, but there's a lot of freight going out of there. And oftentimes for drivers, they refer to those kinds of areas where they have a hard time getting freight out of that area to be called backhauls. So that's the term in transportation we use.
So it's like a challenging situation because, people in Florida need their goods shipped in just as much as anyone else, but the analysis of the graph says, oh well, that's not it's a higher cost area to ship into because of the backhaul. But
yeah, and realizing that is where carriers can be more empowered to negotiate with shippers. Okay, you want me to go to this area that not a lot of freight comes out of, making it harder for me to find my next load? Well, pay me more. Right. So this is the kind of analytics that can help carriers make more sound decisions. So they can still service people in Florida, right?
Yeah.
But if the economics of it doesn't make sense for them, and shippers are not willing to do what they need to do to make it more to create more incentive for the carriers, then yeah, that's an area that you won't get a lot of traffic, a lot of freight activity into. That could be areas where consumers might be suffering. And sometimes because of this, if the shipper and the carrier doesn't come into some agreement about how to settle with the rates and stuff, some of the cost is offloaded to the actual consumers too.
Yeah. Another one. Do logistics companies tend to cross-share their data? So like companies sharing their data with other companies back and forth. Is there, so like in an earlier slide you had, or we have this network and this network and we can analyze them together. Does there tend to be collaborative analysis across companies, or does that tend to stay within the boundaries of each given logistics company?
So I will say that carriers are hesitant to share their data at times. And
I mean, it makes sense. It's
yeah,
competitive advantage.
Yeah, exactly, competitive advantage. So they are hesitant, but there are carriers who are more than willing to share. But obviously, sharing, we don't just naively share their data. They don't just, especially with Trimble Transportation, we don't just naively share data. We have to take lots of steps to anonymize, obscure, and protect our customers, right? Otherwise, we can't have nice things. But once we do that, we do have a product called Market Insights, which collects data from carriers who have agreed to join our program and share their data so that you can actually see like the average rate going from maybe California to Utah, or the average number of orders, or the kinds of shippers you could work with in that area. You could get that kind of data. So yes, we do have that kind of analysis, but it's not really easy to get it there. And there's a lot of steps to make sure that that data is secure and the integrity for it is actually in place.
Yeah, that makes sense. So we're at 1:15 here, so I think we're going to wrap soon. If you've got the time, I've got one more question.
Go ahead.
That's all right. So you've talked about approaches to answering kind of three different but related questions: the efficiency of the network, whether or not to take a tender, and then assigning loads to powers, to the trucks and the drivers. To what extent, in general, can you answer those three questions separately versus having to answer them together because they're coupled? I know it's like the networks is kind of a longer term decision. What routes do we advertise that we ship along, or what routes internally do we price out or assign, versus kind of the the real time decision of accept the tender or not, and the semi real time of all right, who and what is going to execute on it. I'm just curious what the how coupled those decisions are.
In transportation, so I want to just like reemphasize how complex transportation. I've been working in it, and oftentimes I still get frustrated of how complicated it can be, because there are so many aspects about it that are intertwined. there are some latent connections between one aspect of one's business versus the other. And but there is a divide and conquer method that does work well, where you can actually answer the questions separately, and then you can then bring them all together. Not automate. I don't think you can bring them all together in an automated way, because there's too much nuances day to day. That's where humans that's when humans are vital, where you can take the solutions that are provided by each of the problems that are addressed in each of the problems I talked about. And as a human, you can take it all in and really give a holistic solution. So yes, they are pretty coupled. However, you can divide and conquer, answer each question separately, and then take the combination of all those answers to make sound business decisions.
Mm-hmm. And of course, the nice thing about Python is it makes it super straightforward to take that data, take those analyses, tie them together, and present them in a clean way.
Yeah. Exactly. And we really, here in Trimble Transportation, we really rely on Python and its ecosystem to help us answer all these problems. It's been really enjoyable using Python for all of this.
Very cool. I think that's all we've got. Any last words before we wrap?
No, but I look forward to being more involved with the OpenTeams community. So
Terrific.
Look out for your friendly neighborhood data nerd.
We'll be in touch. So great. That's all for today's event. Thanks to everyone for attending. We are recording the event, as you probably noticed, and so we'll get this posted on our YouTube channel as soon as we can. Subscribe there, OpenTeams YouTube, to get notified when that gets posted. If anyone is interested in participating in a similar event in the future, representing a talk or expanded, modified version of a talk about an open source or an open source related topic, please reach out at connect@openteams.com and we'll get working with you. And in general, check out openteams.com to learn more about us and our offerings, and we'll see you next time. Thank you, Nick.
All right.
Thank you, everyone. Have a good one.